It's the holidays and you build a standing desk. So here's a diagram of that desk. On it you have 2 speakers, a monitor, and of course your physics workbooks piled high. So a standing desk is a desk that you can adjust the height of. For example, I have an electronic one, so I push of the button. You can also get ones with like a manual up-down or like a pulley system. So let's assume this one's electronic because that's much more fun. So to build it, you needed to buy the desktop, you needed to buy some standing desk legs, and that's pretty much it. So we're given some information about the load, so the things on top of the desk with mass. And question A, state the conditions required for static equilibrium. So static equilibrium of a system is when, let's do static equilibrium, is when the net force is equal to 0 and the net torque is equal to 0. So what I mean by that is the forces acting up are equal and opposite to the forces acting down. And same deal with left and right, but on a free body diagram, you recall something like that. In this case, the net force is 0 because the upwards force is equal and opposite the downwards force, and so since they're vectors, when we add them together, the resultant would be 0. Right? The forces are balanced. So that's point 1. Point 2 is that the net torque is 0. So torque is like a rotational force. It's force applied a distance away from a pivot point. Right? Like think of a wrench. When you turn a wrench with your hand, it's some distance away from the nut that it's turning. That is a torque. And for the net torque to be 0, we would say that so instead of up and down, we use the words clockwise and anti-clockwise. So we'd say clockwise torque and anti-clockwise torque, or should be torques, are equal in magnitude. And since I specified clockwise and anti-clockwise already, it's clear that they're acting in opposite directions. Right? But just like forces, the torques are equal and opposite when they're acting in the opposite directions. However, to answer this question, all as you need are these 2 statements here. Right? The linear forces add up to 0, F net equals 0, and the rotational forces add up to 0, the torque adds up to 0. Cool, so that is static equilibrium. Part B, draw a labeled free body diagram. Okay, including the weight of the desk. And here it's told us we can assume that the desktop, so the tabletop, has uniform density and a mass of 10 kgs. And we should have 7 forces on our diagram. So here is our desk. Let's start with the easy one, the one that we're given the assumption for. If it has a uniform density for a shape like this, a rectangular shape that's symmetrical, the center of mass will be in its geometric center. So what I mean by that is the weight force of the desk is smack in the middle. So I'll do F desk, right, the force due to the desk. However, if the shape was asymmetrical, like it had extra thickness over there, you can see that the center of mass would actually be shifted to the right. But in level 2, the center of mass is almost always in the geometric center to keep things easy. Cool. And actually, just reading ahead, part C, it says for each weight force, calculate its magnitude. So let's do these two questions together. So I'll just do it on the right. So the desk is mass times gravity. So I'll just remind ourselves, weight is mg. So the desk has a mass of 10 kgs times gravity, 9.8, 98 newtons. All right, one force done, 6 to go. What else is on our desk? Well, of course, we have our physics books, we have 2 speakers, and we have a monitor. So that's 4 more objects imparting a weight force onto the desk. So let's label those and put them in roughly the right position. We can always label the distances after. So actually on top of F desk, there is also F monitor. So I'll put that very, very close to it. And the monitor has a mass of 3 kgs. So 3 times 9.8. What's that? 30 minus 0.6, 29.4. Yep, newtons. Alright, and then we also had the speakers, which were just a bit off center. So we'll do FS1 for speaker 1 and FS2 for speaker 2. Right, use like sensible naming conventions, and it's clear from this diagram what we're referring to as well. And since they're the same mass, I can calculate one of the magnitude and it will be the same as the other. And so the speakers had a mass of 2 kgs each. 2 kgs times 9.8, which is 2 times 10 minus 2 times 0.2, so it's at 20 minus 0.4, 19.6 newtons. So how many do we have so far? 1, 2, 3, 4. Oh, of course, our physics workbooks, essential, and that's towards the left. So F book, with an S, books, because we have so many. And our books had a mass of, I think it was 1 kg. Yep. That's a very challenging calculation. Now we're missing 2. So what are those forces? Right now we have 5 weight forces all acting down. In this case, it would be accelerating towards the center of the Earth very quickly. Right? So what's keeping it up? Well, it is, of course, the legs of the desk. And see in this diagram, there's some overhang. Now, if we were doing this question properly, right, at university level, we would consider the weight force of this part of the desk separately to the weight force between the legs, right, because it'll generate different directions of torque. However, to keep things simple for ourselves, I'm going to essentially chop that bit off. So our legs are at the outermost position of the desk. So once more, in level 2, I've never seen it come up. It could, but I've never seen it come up where you need to account for those side bits, the overhang. If you're like, what are you talking about? Don't worry. If you kind of get what I'm talking about, you should actually try it. You could assume that these overhangs are, let's say, 10 centimeters each, and try to do a full analysis of that. But for our purposes, we're going to take that the legs are supporting the desk right at the edges, like so. Cool. And we can actually draw these arrows either underneath like that, or just to distinguish them a bit, we can put them above. Yep. And what should we label them? Well, we could label FA and FB. So it's pretty common if you have two support forces, like due to legs on a desk, for example, we can call one A and B. So on this diagram, this point here is A and B. Cool. Alright, and can we calculate their magnitudes? No. Right, those are the support forces, which is actually question E. So let's just recap question B and C. So free body diagram and calculating the magnitude of the weight force. So we have two support forces created by the two legs. We have the weight force of the desk and then the weight force of each of the objects on the desk, right, and their rough positions, right, according to the diagram that we were given. And while we're here, we could label the distances, but we'll save that for question E. And the weight force, of course, mass times gravity. Yeah. Cool. And final thing is, our notation was clear. We used subscript, so like F books, F S1, to make it clear we've accounted for everything. Alright, question D. With no further calculations, explain which leg will exert a greater support force. So it's basically asking which leg is holding up more of the weight. So looking at our diagram actually, notice how the weight of the desk and the monitor are perfectly in the middle, which means the legs are holding up the same amount of that weight. Similarly with the speakers, they are perfectly symmetrical. So again, the legs are evenly supporting that weight. However, the books are offset. They are much closer towards leg A, which means leg A will be holding up most of that weight in comparison to FB. So in fact, the support force at leg A is greater than at FB. So we could say FA greater than FB. And this is why we labeled them clearly, so we don't need to write out massive paragraphs. So the support force at A is greater than at B because all weight forces are symmetrical apart from the books, which are much closer to A. This means A supports more of the weight of the books. And if you've never experienced the support force feeling, what you can do is you can grab a ruler, preferably a meter ruler, but any long straight object would do, balance it between your two index fingers and have a friend push in the middle, and you should feel the force acting downwards to be about balanced, and then ask them to push closer to one of your fingers, and you'll feel this imbalance in forces. And that's exactly what this desk is feeling at leg A, because it's supporting more weight. Now, the books aren't that heavy, right, in comparison to everything else, so it won't be that significant, but it's still greater than at B. Part E, using the conditions that we've stated, form equations and solve for the magnitudes of both support forces. So back to our free body diagram, we know all of the downwards weight forces, and we now need to use these two conditions to solve for the magnitudes of A, or FA and FB. So this is called a equilibrium analysis, where we apply these two conditions. And so to do that, we need to make use of both of these. So to make use of the net force, we need the magnitudes, which we've worked out all the magnitudes for the weight forces. To make use of torque, you'll know in your formula book, and that torque is force times a distance. So we need to label our distances. So let's do that first. So this is our 0, that's point A and point B. The disc is 1.8 meters long. Maybe I'll just make a copy of this diagram, actually. Make it a bit bigger. The benefits of working digitally. Alright, beautiful. So, and actually here, in this case, having the force, all the forces, use my words, having the forces all on the bottom side lets us draw the distances on top. So I'm going to do that. Again, this is just to make it more readable for you, however you do it, as long as you can keep track of your forces and your distances clearly. So we have .8 meters for the full length of the disc, which means halfway would be 1.8 divided by 2, which is 0.9. And that would account for the weight of the disc and the monitor. I see we still have 1, 2, 3 weight forces that don't have a distance from A. So let's work those out now. So the physics workbook is 10 centimeters from the left leg. And a reminder, we've labeled our left leg as A. The speaker is 30 centimeters from the left leg. The second one is 30 centimeters from the right leg. Okay, so let's work that out. 10 and 30. So speaker 1, 30 centimeters from the left leg. Speaker, books, 10 centimeters from the left leg. And speaker 2 was 30 centimeters from the right leg. So how are we going to calculate that? So this distance is 30 centimeters, which means we go 1.8 meters to the right, and then we subtract 0.3 meters, which would give us 1.5 meters. Up to speaker 2. Right. So looking at our diagram, we have our forces clearly labeled with arrows indicating their direction, and we worked out the magnitudes up above. So actually I'm going to add those in next. And we've clearly labeled the distances. How I've drawn it is a nice way to keep track of it, because it goes from longest to shortest, so it's very clear to see. Yeah, not the only way though. So let's write down our first equilibrium condition that we'll use. The net torque about a point, in our case about A, must equal 0. So a reminder, torque is a force applied at a distance from a pivot point. And in our case, the two legs, the two supports, are the pivot points, and we need to choose one of them. So you could have chosen B and worked out the distances going the other way. Absolutely fine. I just chose A in this instance because we're actually looking for both FA and FB, so it doesn't really matter. If we were looking just for FB, you'd want to choose the pivot point at A, because the torque at A cancels out because it's at a distance of 0. Anyway, let's apply our condition. So, oh wait, before that, what was I doing? Yes, getting these values. So desk was 98 newtons. The books were 9.8 newtons. The monitor was 29.4. And the speakers were 19.6. Right, so we have everything we need on our diagram. It is worth spending the time drawing a perfect diagram so you don't get lost in the calculations. So let's not get lost in the calculations then. So the torque about A. So let's do the clockwise torque about A. So clockwise being that direction. So let's have a think. We're starting at A. What forces are going to want to rotate the desk this way? All of those weight forces, right? Whereas the support force on the other side is want to push the desk back up the other way. So let's account for that. So what do we have? We have F books times the distance of the books from the pivot point. To that we will add F speaker 1 times the distance of speaker 1 from the pivot point. To that we will then add F desk, the distance of the desk's center of mass from the pivot point. Then we have the monitor weight times the distance of the monitor from the pivot point, and finally F speaker 2 plus the distance of that speaker from point A. So I've very clearly shown using symbols, which is why we were careful with our naming, the clockwise torque about point A. Now let's substitute in the values. So the books, weight is 9.8, distance 0.1. Speaker 1, 19.6, and that was 0.3 meters from the pivot point. The desk, 98, what was that, 0.9. Weight of the monitor, 29.4. Distance was also 0.9. Weight of the speaker, 19.6, but this distance was 1.5. Right, so we have 1, 2, 3, 4, 5 torques created by the 5 weight forces acting on the desk, including the weight of the desk itself. So 9.8 times 0.1. So that was the torque created by the book. To that we will add the next one, 19.6 times 0.3, yep. I'll just add them one at a time so I can see all the numbers as I go, but feel free to just do it in one go. Next was 98 times 0.9. Next was 29.4 times 0.9. And finally was 19.6 again, but this times 1.5 meters. 150.92. And units for torque, force times distance, newtons times meters. So that is our clockwise torque about point A. To find the net torque, we know we need to find the difference between clockwise and anti-clockwise. In fact, we need to set that difference to be 0. But let's find the torque anti-clockwise about A. Back to our diagram, what is going to want to rotate our desk anti-clockwise? It's the only force acting upwards on the right hand side of the pivot point is FB. So this one's quite easy actually. The torque is the force FB times the distance 1.8 meters. So FB times 1.8 meters. And in proper mathematical notation, we would put the coefficient first and then the variable second. Right? And remember, FB, we have no idea what it is. That's why I haven't put in a magnitude, a value, like we have with the weight forces before. Now, how do we use this condition? Well, what it means is that the clockwise torque is equal to the anti-clockwise torque. So the clockwise torque is equal to the anti-clockwise torque. So setting 150.92 equal to 1.8 times FB, we have formed an equation with one unknown, FB, so we can solve. So we'll divide both sides by 1.8 to give us FB equals 150.92 divided by 1.8, 83.84444. 83.8, which rounded, what are we going to round to? Guess it's got to be one significant figure because our distances are given as one significant figure. 80 newtons. Right? But we keep our unrounded version for further calculations. So back to our diagram, we've worked out FB as 83.844 newtons, unrounded, by using the net torque equals 0. Okay, so now how do we find FA? We could compute all the torques again, but from point B, right? So go the other way, but that seems like a lot of work, right? We'd need to set up the distances again, but going from B towards A. So more simply, we can actually use the second equilibrium condition, which says that the net forces must equal 0. And what we mean by that is the forces acting upwards are equal and opposite to the forces acting downwards. So actually, let me use a different color for that one. So all of these weight forces acting down, we'll add them together, and the support force at A and B must add together to be the same value, right? Because they're going in an opposite direction. Let's do that now. So F, what do I want to do? F up. No, we'll do down first. Let's be specific. So it's the net force down. So we're finding the total force acting down. It would be the sum of each of these weight forces. So what's that? 9.8 plus 19.6 plus 98 plus 29.4 plus 19.6. Double check. Yep. 176.4. That is the total weight force acting down. And we know the upwards force is FB plus FA. So FB or FA plus FB. However, FB we've already worked out. And we know the equilibrium condition is that, actually this word net is confusing me, that the force upwards, total force up, must equal total force down. So FA plus 83.844 must equal the force down, 176.4. Again, we formed another equation with one unknown, so we can solve, in this case by subtracting 83.844 off of 176.4. $83.844. 92.556. Which again, rounded to one significant figures, would be 90 newtons. And there we have it. So let's go back to the question, make sure we've answered it. Using the conditions, yep, so we use both conditions. Right, first we use the net torque to find FB, then we use the net force to find FA. So we formed the equations and we solved. Yep. And the directions of the forces we also gave in our diagram, but we could always just say that it was what FB was acting up and FA is also acting up. Right, because a force is a vector, it needs a magnitude and a direction. All right, and lastly, now, of course, after all that hard work, you decide to use the standing desk, and it gains a height. Right, you push a button and it starts moving up. So it goes from rest, so like stationary, and then it gains a constant speed of 5 centimeters per second. And it takes 1 second to achieve that. Right, so it's accelerating to get to its terminal velocity, right, its constant speed, as it gains height. Part 1. Explain why the desk is initially no longer in static equilibrium. So let's remind ourselves, for static equilibrium, the net force must be 0. So net force equals 0 for static equilibrium, and of course the torque. However, when we push the button, when activated, the desk accelerates up. Now, to accelerate, this means that the net force does not equal 0. Right? By Newton's second law, F net equals mass times acceleration. For an acceleration of something with mass, it needs a net force to push it, to get it going. So, therefore, not in static equilibrium. Easy as that. Right, so once more, we know the conditions for static equilibrium, but applying them to a context, we just think for a moment, alright, is it accelerating in any direction? If it is, it can't be in static equilibrium. Is it accelerating by rotating in any direction? Well, then it can't be in static equilibrium because the net torque won't equal 0. Right, that was the other condition. In this case, we assumed that the legs both pushed up at the same rate, so we didn't use that condition. And then part 2 was explain why it reaches static equilibrium after 1 second. So, static equilibrium. So after 1 second, it is now traveling at a constant speed, right, of 5 centimeters per second. And we know for an object, in this case a desk, to travel at a constant speed, the net force must be equal to 0. So let's write that. So part 2, desk traveling at a constant speed, therefore not accelerating, therefore net force is 0, and we do assume that there's no torque generated as well. Once again, we assume that the legs both push up at the same rate, rather than one leg being like super powerful and exerting a massive force and breaking your desk, which does happen if you don't program the controller properly, but we did in this case assume that. So let's just say assuming net torque is also 0 as legs push up with the same force. Right? And all of these conditions mean desk is in static equilibrium. And there we have it. So hopefully you took a few things away from this. I think for me, the biggest thing in answering this question accurately is a good diagram. So take your time, honestly use your ruler, it makes it so much clearer. Clear labels, show the magnitudes of all the weight forces, show the calculations. Yeah. Alrighty, well have a great rest of your holiday if you're on holiday, and if you're not, I'm so sorry. See you next time.